As described in the previous YouTube movie clip, the interaction of electromagnetic radiation with atoms, molecules, and macromolecules may result in 1. No absorption if the energy of radiation does not match the delta E that separated excited state from ground state. 2. Absorption occurs if the energy of the radiation matches the delta E that separates the excited state from the ground state. 3. Diffraction or rotation of light. Both UV visible absorption and CD spectroscopies are similar in that they are based on the absorption of UV light by the electrons on their way up to the excited state. Fluorescence spectroscopy, on the other hand, is based on emission of light by electrons on their way down to ground state. Although both UV visible absorption spectroscopy and CD spectroscopy are based on light absorption, they differ in that CD uses polarized light rather than non-polarized light. A CD spectrum measures the difference in absorption between left and right circularly polarized light by molecules. Now let us examine what polarized light is. In everyday life, many people are familiar with polarized sunglasses. When comparing photos taken with and without a polarized filter, one may notice that images taken with a polarized lens show little or no glare. Electromagnetic radiation exists in several forms, including gamma rays, X-rays, UV, visible, infrared, microwaves, and radio waves. These forms differ from one another in wavelength and energy. However, regardless of the type, all electromagnetic radiation travels at the speed of light. Another property of electromagnetic radiation is polarization. Light, or electromagnetic radiation, consists of oscillating electric and magnetic fields that are perpendicular to each other. However, because only the electric field interacts with molecules in CD spectroscopy, the magnetic field will be ignored in the present discussion. Light that we observe from the sun travels to the Earth in all directions and therefore is unpolarized or randomly polarized. These unpolarized lights, however, can become polarized when they were reflected from the surface of an object, pass through a Polaroid filter of a camera, or polarized sunglasses shown. Depending on the direction in which electric field oscillates in respect to the direction traveled, electromagnetic radiation can be classified as 1. Non-polarized, 2. Linearly or plane polarized, and 3. Circularly polarized light. In non-polarized light, the electric field oscillates randomly in all directions perpendicular to the direction of propagation. In plane polarized light, the electric field oscillates in a single plane. For example, along the x-axis or along the y-axis. In circularly polarized light, the tip of the electric field vector rotates in a spiral, producing either right-handed or left-handed helices. To understand polarized light, one needs to familiar oneself with wave equation. As a wave, the motion of light can be described by the equation y is equal to a, multiplied by sine of 2 pi nu t plus phi, where y is the displacement of the wave, a is the maximum amplitude, t is time, and nu is the frequency. One way to interpret and visualize this wave equation is as follows. In the diagram shown, the y-axis represents wave displacement, whereas the x-axis represents time. Because this is a sine function, the motion begins at zero displacement. In contrast, a cosine function begins at the maximum displacement. The term 2 pi indicates that the wave repeats itself every 2 pi radians, or 360 degrees. Since the maximum value of the sine function is 1, the maximum value of a, multiplied by sine of x, is equal to a. The phase constant, phi, tells us the initial phase of the wave. If phi is equal to 0, the wave begins at zero displacement as shown in this diagram. The phase constant indicates how far the wave is shifted from its initial position. In CD spectroscopy, because we're concerned with the oscillation of the electric field of electromagnetic radiation rather than the displacement of the sound wave, the equation can be written as shown. Here, Ex and Ey are electric field components traveling in the z direction and oscillating along the x and y axes, respectively, where E is the electric field at a given time. E0 is the maximum value of E. Lambda is the wavelength, and c is the speed of light. The c in this equation indicates that one is dealing with electromagnetic radiation that travels at the speed of light with a specific wavelength of lambda. For plain polarized light traveling in the z direction, its electric field can be presented as a resultant wave, which is the sum of its x and y components. If its x component is 0, then the electric field oscillates vertically. If its y component is 0, then the electric field oscillates horizontally. For circularly polarized light, the electric field can be viewed as a resultant wave formed by the sum of its x and y components. Unlike plain polarized light, where the x and y components are in phase, the two electric field components of circularly polarized light differ in phase. One component, for example the y component, travels 1/4 of a cycle or 90 degrees ahead of or behind the x component. Thus, when the two components combine, the resultant wave is the left circularly polarized light and rotates in the counterclockwise along z direction as it moves in space. A plus sign in the equation means rotation occurs in the counterclockwise direction, and the resultant wave is a left circularly polarized light. A minus sign means rotation occurs in the clockwise direction, and the resultant wave is a right circularly polarized light.